All right, next we want to move on to the second parameter that we want to discuss about, which is the population total. Since we know that the population total tau is equals to the population total size n multiplied to the population mean, capital Y bar. So if we want to estimate the population total tau using the tau hat, so we use our sample equals to the population size n multiplied to the sample mean. Let's say, for example, if I want to estimate the box of oranges. So a box, let's say we have 100 oranges. I want to estimate what's the sugar content of all of the oranges in the entire box. Then I'm not going to cut out each of the oranges, 100 of them, to measure the sugar content. Let's say I take a sample of 5 oranges and estimate our sample sugar content, and then we can find per orange sugar content is about 65%, let's say. Then we can multiply to the total number of oranges in the box. Then we can estimate what is the total sugar content in the box of oranges. Okay, so the expected value of the tau hat is equals to n times y bar, and expected value of n times y bar, n is a constant, so it's still n. Expected value of y bar is indeed mu, so this is the unbiased estimator of tau. Variance of tau hat is equals to the variance of ny bar. N is a constant, so that becomes n squared multiply the variance of y bar. So that means if we have already estimated the average from the sample, we can simply multiply to n to find the total, or to n squared to find the variance of total. Okay, so the confidence interval would be tau plus or minus the critical value multiplied to the square root of variance of tau. So square root of variance of tau is indeed to get the n's out, and then we have the square root of variance of y bar. And this is n times y bar, so we can also take out n from the bracket. Again, if we have already constructed the confidence interval for y bar, simply we can multiply the whole thing by the population size n. Then we find the confidence interval for the population total estimate. Alright, so go back to example 3.8 with the survey on the number of persons in the populations of the households. We know the total number of households in the area. We only sample 30 of them. Okay. Last time we calculate what is the average number of person per household. So that's what we have done previously. Average number of persons in a household. So y bar equals to yi times the fi, and adding them up, the frequency of it, and then divided by the total household that we survey. So that's around 3.47 persons per household. We construct the confidence interval for our point estimate. Now we can also use this relationship to estimate the total population. So we have 3.47 per household. Now we have 14,000 households. Then we can estimate the total population. Then we can also find the confidence interval by multiplying the total number of households to the confidence interval for y bar. Easy enough. Okay. So what if we know that the number of 4-person household is 4848? What is the standard error of the new tau? If that's the case, number of person 4 and the sample could be taken out because we know it for sure. So now the population size is reduced to 10,000. The sample size, number of household we visit, is down to 21. So based on the 21 household, we can estimate the number of person per household is around 3.2381. So if we multiply that to new capital N, we can estimate that's about 3 32,381 population. But indeed, the total population is this estimate value plus the one that we know, right? So 4 person per household, and those are about 4,848 households with 4 persons. So now we have 51,773 population. So only this part have the variance. This part we know it for sure, so this part does not contribute to the variance. Okay, then we need to calculate the SY square based on our sample. So we need to recalculate the new variance for my sample without the 4 person household. It's around 1.9905. The critical value at 92% confidence interval is 1.751. So putting everything together, we find that is the new confidence interval for the tau. Another example, 3.10. An industrial firm is concerned about the time per week spent by scientists on certain trivial tasks. We have a log sheet of alpha of a simple random sample, n equals to 50 employees. So the average amount of time spent is about 10.31 hours. And then we have the sample variance is 2.25. Now we have the total employees 750. So on average per employee, based on our sample, we have 10.31 hours of time lost based on the 50. So per person is about 10.31. So now we have 750 employees. Total time loss is about 7,732. A point estimate is not good enough, so we also want to talk about the errors. The standard error is defined as the square root of the variance. The variance is equals to n squared multiplied to the mean variance. Okay, so the standard error is about 153.7. Confidence interval for the tau is equals to our tau estimate plus or minus the margin of error. Okay, 3.11. A population of network in a shopping mall. Let's say there are 243 retail shops, and then we want to estimate the total sales for the coming year, in year 4, let's say. And then we want to see how large a sample size of n is needed so that the estimate of the total sales is within 10% of the total sales. So first of all, we want to estimate what is the new year 4 tau. And then we want to say that I want to be sure that estimate is good enough, that the bound of error is 10% within that total sales estimate at 95% assurance. And we are given some of the data, the last 3 years total sales, and also we're given the variance or SY, but this is not the variance of the total sales. This is per retail shop's sales data. Okay, because this is SY. So we're given the standard deviation of the sales per retail shop. This is SY. Okay. Now, this is the question. We haven't done the survey. We want to determine the sample size with the past data. Then how are we going to do that? This usually happens when we try to conduct a sample survey. We haven't the first parameter, the first variable we ask is what is the sample size we want to collect, right? So based on some of the data on hand, how can we assess that estimate? With the 3.10, previously we talked about the mean. We derive a formula saying the sample size could be correctly assessed by N0, N naught depends on the variabilities of our y bar, our sample mean, and also d square. D is the bound of standard error. D equals to bound of error divided by the critical value. Okay, so make sure you don't confuse with D and B. D is the bound of standard error. B is the bound of error. Okay, so D, I should write that. D is equals to B over Z. We need to divide that by the critical value. All right, so we have these when we are dealing with the sample mean. And then we know that the relationship between the total and the sample mean is N. Okay. So we can go back to this same process of the formula, and then we find that N naught for tau, the total, is indeed equals to N squared multiplied to SY squared over D squared. Okay, so that SY squared is referring to the per retail shops variations. If we are given this is S tau, then that we are already having the variation of the past year's total sales, then we can simply use this relationship to find the N naught. But now this SY or this SY is referring to per retail shop. Okay, so that's why we need to multiply to N squared. D squared is bound of error, B, divided by the critical value. Okay, so we know the total number of retail shops, 243, 95% assurance, so we know the critical value, which is 1.96. Question is, what is SY and the bound of error? Okay. With the historical data, we can see on the variations is around 0.8. So we can simply take an average of SY of the past 3 years to substitute into the SY. Okay. Next one is, what is the bound of error? So the requirement is that the estimate of the total sales is within 10% of the total sales. So the bound of error would be the 10% of the total sales. So we can estimate the total sales for year 4, then multiply by 10%, that would be the bound of error, right? So let's look at the total sales estimate. First of all, we can see a constant growth. So a good guess of the next year total sales is around 420. And then we're told that the bound of error is about 10% of it. So let's put 42, which is 10% of 420. So now we have everything. We have an average of SY. Then we can substitute into the formula. We find the first assessment of the sample size. Very quick guess is 82. So if we collect 83 retail shops data, that would be good enough to satisfy our bound of error and the requirement for the assurance. But don't forget, N naught is just the first assessment. So we can correct it by N naught corrected by 1 plus N naught to N. Indeed, sample size of 62 is already good enough to satisfy our bound of error and the assurance requirement. So 62 is a better figure. If both of them satisfy our requirement, why take 20 data more, right? We want to save the money and the time resources. So 62 is good enough. We can also see there's a big difference between 62 and 83, because if we look at N naught to capital N, this is a significant ratio. Okay, if N naught as compared to capital N is insignificant, let's say N is 1,000 or 2,000 in the population, this ratio is insignificant. So 1 plus 0 is 1. So N naught is a good assessment. Oops. Okay, so that's the population estimate.